Howdy, students. In my opinion, this is one of the most important videos this semester. In it, I'm going to talk about how we can build an energy system that provides cheap and reliable power using climate-safe, renewable energy. This is important because you've heard a lot this semester about how bad climate change is going to be. But you'll probably ask yourself, can we do anything about it? The answer is yes, but it's not something that most people understand. I can't tell you how many times we're talking about renewable energy to someone and they'll respond, the sun goes down at night. What are you going to do then? It turns out that scientists have been working on this problem for many years, and we understand how to build a reliable energy system that runs mainly on renewable energy, allowing us to solve the climate problem. That's what I'm going to be talking about here. So let's begin with the definition of a term called capacity factor. The capacity factor is the ratio of actual output of a generator to the maximum output it could produce. So if you have a wind turbine with a maximum capacity of 6 megawatts, when the wind is blowing pretty hard, it'll generate 5 megawatts, and the capacity factor is 83%. Later in the day, the wind isn't blowing so hard, and the wind turbine is only generating 1 megawatt for a capacity factor of 17%. For a real-world example, the Three Gorges Dam in China, the largest power generating station in the world, has a maximum capacity of 22.5 gigawatts. That's equal to about 22 coal-fired power plants. In 2015, it generated 87 terawatt hours of electricity for a capacity factor of 45%. Why might the capacity factor for that dam not be 100%? There are a few reasons. First, there may not be enough demand. When demand is low, the operators run less water through the turbines, generating less power. Second, if there's a drought, there might not be enough water behind the dam to run the turbines at full power. Now that we've covered this background, let's examine some different scenarios. I'm going to use the website model.energy to estimate the cost of different grid configurations. This model includes a bunch of assumptions and configurations that I won't go over here because the general answer doesn't depend on them. For the purposes of this example, let's assume we're focusing on the United States and we need to generate 100 megawatts of power. That's about as much power as a small city would use. Let's start off with an electrical grid that's 100% natural gas, which is the cheapest fossil fuel. With 100% gas, the model generates power at a cost of 56 euros per megawatt hour. Now let's compare the cost of this 100% natural gas grid to the cost of different grid configurations to see if we can produce climate-safe energy at a similar cost. For our first clean grid, let's see if we can generate 100% of our power from wind. The model tells us that the cost of electricity on this grid is 218 euros per megawatt hour, or 3.9 times more expensive than a 100% natural gas grid. Why is this wind grid so expensive, you ask? The answer is that wind's capacity factor varies over time. When the wind is calm, the capacity factor may only be 5.5%. Because people insist on having power 24/7, it is this lowest capacity factor that determines how much power you need. With a minimum capacity factor of 5.5%, you need 1,800 megawatts of wind in order to ensure that you always generate 100 megawatts. In other words, you have to greatly overbuild your grid. When comparing to natural gas, realize that natural gas is what's known as dispatchable, meaning it can be turned on and off. Thus, the capacity factor can be 100%. So to generate 100 megawatts of power with natural gas, you only need to build 100 megawatts of generation capacity. So even though wind and solar energy are cheaper, you have to build so much excess capacity with wind that it ends up being much more expensive. What about a 100% solar grid? Well, you can't do it. At night, the capacity factor goes to 0 because there's no sun. So there's no way to generate all of your power with 100% solar energy. What about a combination of wind and solar? The model finds an optimal mix is a system that produces power at a cost of 143 euros per megawatt hour, about 2.6 times more expensive than 100% natural gas, but 50% cheaper than 100% wind. In this optimal solar wind grid, you need 1,100 megawatts of wind and 160 megawatts of solar energy in order to ensure that you always have 100 megawatts of electricity. The cost of this grid is lower than 100% wind because you don't need to overbuild as much. The reason is that wind and solar tend to be anti-correlated. Very sunny days, when solar is doing well, are often the least windy. By combining different renewable sources, the minimum capacity factor of the system is higher, so you don't need to build as much. What if we add batteries to the system? With batteries, we can store power generated when the wind and sun are abundant, and then feed that power to the grid when the wind and solar are not producing. In that case, the cost of energy drops to 64 euros per megawatt hour, which is about 10% more than the cost of a 100% natural gas grid. The reason is that the batteries allow you to build even less renewable energy than in a grid without batteries, because the batteries are dispatchable. They can cover at times of low renewable output. What I've shown y'all is a simplified demonstration of how you construct a clean, reliable grid from renewable energy sources. Several major research projects have analyzed the energy system in greater detail and with more accurate assumptions, and they found basically the same thing that I showed. We can build a climate-safe energy system that can sell energy at about the same cost that we're paying today. Now, what everyone finds is that the keys to a clean energy future is a grid that is mainly wind and solar. This reflects the fact that wind and solar are now our cheapest energy sources. But you also need some type of dispatchable power, which is power that's always available. In our last example, it was batteries, but it could also be, for example, hydroelectric or nuclear power. To summarize, I said at the beginning of this video that it was one of the most important videos this semester. The reason is that it's easy to look at the climate problem and get depressed. But what we've shown here is that this is a solvable problem. We can reduce our emissions of carbon dioxide to the atmosphere without raising the price of energy. And this will allow us to solve the climate problem. It's just a question of whether we can muster the political will. And now, your moment of dog.